Okay, last one. So we have this, which definitely has some sticker shock. What? But look a little closer at the pattern. Cosine x, cosine 2x. Sine x, sine 2x. So x and 2x are repeating. So it's like an A and a B, an A and a B. So cosine A, cosine B, sine A, sine B. Hopefully that sounds a little familiar with that 4.2 homework. So cosine of A and B is cosine, cosine, sine, sine, AB, AB. If this was a plus, this is a minus. If this is a minus, which, here, let me make that a little more. If this is a minus, then this is a plus. Since we have a plus, this perfectly matches the pattern of cosine A minus B. Cosine A, cosine B, plus sine A, sine B. So this is equivalent to the cosine of x minus 2x. And this is still equal to the square root of 3/2. So that first impression is like, what? And then you're seeing the 2x's and your brain may have been like, are we supposed to use double angle identities? No. I mean, we could have, but it would have made things really ugly. But the odds of you actually seeing this occur, though, pretty slim. All right, so x minus 2x, well, 1 minus 2 is -1. So this is really just saying, well, the cosine of -x equals the square root of 3/2. Now, with cosine, because cosine is even, it absorbs negatives. But I'm going to leave it because if it was sine, that negative would have an impact. So we'll just leave it. Like, it's not going to hurt anything to leave it here. It just means we have an extra step later on. Several, actually. All right, so where is the cosine square root of 3/2? So that is long side. So this is long short. That is 30 degrees, which is pi over 6. STC. And 11 pi over 6. So pi over 6 plus 2 pi k, 11 pi over 6 plus 2 pi k. But the angle in question here is -x. So those negatives now, I have to divide them. So the same way I did earlier with the 2, I divided by 2 on both things on the right. We have to do the same thing here. Which all dividing by -1 does is change the sign. So I have negative pi over 6 minus 2 pi k and negative 11 pi over 6 minus 2 pi k. All right, so negative angles are not between 0 and 2 pi. So what I need to do here is I need to add positive 2 pi to these guys. It's still minus 2 pi k. That is actually the same as plus 2 pi k because the k's can be negative. But based on the formula as I wrote it, if I use k equals -1, I will get negative pi over 6 minus 2 pi times negative 1. So this will be negative pi over 6 plus 2 pi. Which 2 pi is really 12 pi over 6. So we get 11 pi over 6. And then over here, same song, second verse, it'll be negative 11 pi over 6 plus 12 pi over 6 is pi over 6. Because it is cosine, we ended up with the things we had before we divided by the negative 1. That is the only reason why we're getting equivalent answers. If it was sine, the answers would be a little bit different, but final answer between 0 and 2 pi is those two guys. I was more just doing that to show you, like, if we leave it in there, it's still going to work out the same. We just might have to do a little more thinking. So that's all, like, half the stuff we learn about is it's just, you know, a nice coincidence. And then this guy, it looks like a double angle, like, but then it's equal to cosine theta. So, well, this is going to be kind of silly. Just looking at it, I can tell you for sure 0 will be an answer. Because 2 times 0 is the same as 0. Then it's a question of, well, is there anywhere else where this would be the case? I don't know. So cosine 2 theta, though, like, yeah, I can't make these jive together easily, even though they're both cosines, like, eh. So if I look on my list of identities, cosine of 2 theta is also equivalent to 2 cosine squared theta minus 1. So there's 3 different things that cosine 2 theta is equal to. The first one is cosine squared minus sine squared. But then if we use our Pythagorean identity, sine squared plus cosine squared equals 1, and substitute in, we can get it all in terms of cosine, which the cosine will be up front, positive, just the way it is in the first cosine 2 theta identity, or 1 minus 2 sine squared theta. If we plug in, so it's all in terms of sine, then it's still in the same position as the minus sine squared in the original cosine. It's minus 2 sine squared with a 1, but we wanted the cosines. All right, so ugly 2u squared minus 1 equals u. So we minus the u. So this is 2u squared minus u minus 1 equals 0. So multiply to negative 2, add to negative 1, negative 2 and positive 1. So here, change this out for minus 2u plus 1u. Recopy. Factor by grouping 2u. U minus 1. They have nothing in common, so I put a 1 as a placeholder. U minus 1. Because technically things that have nothing in common always have a 1. It's just, most of the time writing that 1 isn't helpful. This is one of the few times where it actually is. And then our common u minus 1, and then the leftovers 2u plus 1. So we need to know when is u1 and minus the 1, divide by the 2. When is u negative 1/2? So now rewind. U is cosine theta. So when is cosine theta equal to or equal to? What was it again? 1 and negative 1/2. All right, so cosine is 1 at 0, which remember at the beginning I said 0 is going to be an answer. So theta equals 0 plus 2 pi k. And then over here, negative 1/2. So when the cosine is negative 1/2, that's the short side, but it'll be quadrants 2 and 3. So short side, long side, short side, long side. That is our 60 degrees, pi over 3. So this is 2 pi over 3 and 4 pi over 3. So that is the other things theta could equal. 2 pi over 3 plus 2 pi k. And 4 pi over 3 plus 2 pi k. They say solve it exactly, so that is our answer, all 3 of those. So we have 0, 2 pi over 3, 4 pi over 3. Then the next smallest angle would be 2 pi. And then we would have 8 pi over 3 and 10 pi over 3. And it would just keep going. A very ridiculous list of answers. And that is the end of the ridiculous, oh my god, crazy trig equations. Does on occasion happen that you will use this. It's kind of rare, but it does definitely solidify all your algebra working with the trig functions, which that you do have to do in Cal and Pre-Cal. So while in and of itself not that useful, the skill of doing them both together is very useful.